Today I'm going to explain the particular data structure in Bluetooth that is used in Service Discovery Protocol specification. I am referring to the data element. The data element is a header. The data element always exists because a header is mandatory. Followed, Following the header is the payload. It could be either a string, a UUID, a boolean, and so on. But within this first byte, which is the data element, is split into two parts. There's a 5-bit type descriptor, and then the remaining 3 bits is the size descriptor. Now this particular data element describes two things. It describes or conveys the size of the payload, and then it conveys additional semantics, what the payload is representing. Very important things, right? How big is the payload and what is the payload? Eventually, everything are just sequence of bytes. So we need additional semantics to understand what those sequence of bytes are representing. So two things that it's representing. The data element is describing two things, size and semantics. You can see here that if the type descriptor is 4, then it is a string. We know like the name of a person or any English sentences a string, right? However, we know that a string could be indefinitely long, right? It could be one paragraph, one word, an entire book. And that is why the size of that string is described by the size descriptor. So the data element, I will repeat, describing two things, the type and the size. For example, if the type descriptor is 5, then that would mean that it's a boolean. However, underneath it is just a byte, but what that byte means is that that byte is a boolean. And we know that it's a boolean because the type descriptor is 5. If the payload is an unsigned integer, which is by the keyword unsigned, which means only positive integer, like the count of how many persons are in a room, everything is a positive, so it's an unsigned integer. It is represented by the type descriptor 1. The type descriptor and the size descriptor has this type of constrained relationships such that the type descriptor is constraining the size descriptor. What I mean is if the type descriptor is 2, then it only allows the size descriptor to have a value of either 0, 1, 2, 3, and 4. Again, if the type descriptor is 3 this time, then it only allows a size descriptor to have a value of 1, 2, or 4. Now you might wonder, we know that UUID is a 4 bytes size data format. But we can see that it could be either 1 or 2. This is not the size descriptor is not the size of the payload. We the size descriptor is we still need to index the size descriptor into its own table here. So take note of this 1, 2, 4. This is 1, meaning that the payload is 2 bytes. This is 2, meaning that the payload is 4 bytes. And this is 4, meaning that the payload is, yep, 16 bytes. Okay, I was mistaken there when I said the UID has 4 bytes. So the 1, the 2, and the 4, these are the index represented by here. And the payload is described by the data size. Now the additional index in these cases are 0 because the payload is already well defined. For example, the payload is already known to be 16 bytes. The payload is already known to be 8 bytes. For example, in a Boolean that is represented by 1 byte, I know it's wasteful. Boolean could have been represented by a 1 bit, but as byte is the smallest unit in memory, computer memory, then 7 bits of those is wasted just to store either true or false. Anyway, let's see the size index of 5. Let's go back here, 5, 6, or 7. For a type descriptor of 4, which is a string, the valid size descriptor index is either 5, 6, or 7. Let's go to these 5, 6, or 7. 5, 6, or 7. In the case of 5, there is an additional bits of 8. Okay, if you compare this, the additional bits have all been 0 for the first rows, but then for the size index of 5, as there is an additional bits of 8, this is because it is this type is already a string, and a string could be of any length, and that length is described by 8 bits. So it is a string of either the maximum is 255 characters. Now, as soon as the string gets bigger, then the size index could be 6, and the length of that particular string is now conveyed by an additional bits of 16. So 2 to the power 16, that will be the size of the payload string, and so on up to 32 bits. So the additional bits is data structure is a particular section, piece of additional data following the data element, and it only exists for certain size index, such as in the case for 5, 6, and 7, wherein the additional bits is now to exist, which now further describes the size of the payload that is to follow. In other cases, such as when the additional bits is 0, the payload is of well-known size as denoted by this table. Let's go back here. Those I just described the portions where the size has been described by the protocol. The type is is also described by the type descriptor. Like if it's 4, then it's a text string. If it's 3, then it's a UUID. If it's a 6, then it's a data element sequence. Now this now looks like some sort of recursive data structure wherein a member of the data element could be a data element. If it is 7, then it's now a data element alternative. Compared it to here, which is a data element sequence. A data element alternative is, you can think of it like the gender, wherein we have three elements like male, female, and transsexual, right? But only one of them is to be chosen. It could be a male or a female. So it is a list of elements, but only one of them is to be chosen. Hence, the term is data element alternative. This concept also exists in the XML standard. XML can represent a similar idea, where there are options, but only one is to be chosen. Again, a sequence is a list of things, such as your grocery list, taken as a whole. Data element alternative is a list of things, but only one of them is to be chosen from. You can see now that the data element also conveys a certain level of semantics on what those bytes means. And then we have a URL. If the type descriptor is 8, then it's a URL. And then for the rest of the possible values of how much 5 bits can represent, which is 32, for those other values, they are not defined and they are marked as reserved. So let's go to the example here. In, in the case where the type descriptor is 0 and a size descriptor is 0, then this can only be represented as 1 byte. This is the nil type. This is a special case. Let's go back. The nil type. And it's been described here. Supposed to be, if the additional bits is 0, the payload is 1 byte. But since it is a nil type here, 0, then the data bytes, the payload is 0 bytes. If it could have been a boolean, such as this one, 6, wherein the size descriptor is 0 here, then, then that would be the case wherein the payload has a 1 byte size. Of course, we know that a boolean could have been represented as 1 bit, so you are correct to think that 7 bits of this is wasted. But it's unavoidable as 1 byte is the unit in the computer. Let's go now to how to represent a 16-bit unsigned integer. So the type size is 2. Go back to the table, 2. So it's telling us the semantics that it's assigned to complement integer. The allowed size descriptor is either 0, 1, 2, 3, 4, and here it choose 1. If we go back to the table, it's here 1, which means the payload is 2 bytes. So that would be the size of a short. Again, the additional bits is 0. Most interestingly, and I think this will explain the entire protocol, is when how to represent a string. In this example, hat or apple or a sentence or a book. Okay, a data type payload wherein the size is unknown. Let's go. So the type descriptor is 4. Let's go back here, 4, and indeed it is conveying that it's a string. 4 further has a constraint that the size descriptor can either be 5, 6, or 7. So here it chooses 5. We go back to the table here, 5, which means that there is an additional bits of 8. And the data size is contained in the additional 8 bits, which are interpreted as unsigned integer. So these additional bits of 8 here means that the string could have a maximum of 255 characters. It's only a hat here, okay? but it it could be any string larger than head up to a maximum of 255 because the size descriptor is 5. And the size of the head, which is 3 letters, is described by the additional bits and 3. So no null terminator here. Everything is size described. So you can see now that the data element can represent any arbitrary data of any size, of any allowed size, up to what is practically allowable by the system, up to 2 to the power of 32. And then in addition, the data element also conveys what those bytes mean or semantics. Uh, at the at the lowest level, they are just bytes, but the data element can also describe what those bytes can mean. If it's 5, then we know it's a boolean. If it's 1, then we know it's an unsigned integer. In conclusion, the data elements conveys two things. It conveys semantics. It could be a string, data, UUID, and it conveys size. And the additional bits column is a little bit tricky to understand at first, but that's why I'm creating this video to to remind me the the how to interpret the data.